So in this talk, I want to frame this question: where do distances come from? So I'm going to start with a game for you. So the question is going to be, how similar or different are two images? And this is kind of the fundamental question that I've been interested in. How can we measure distance between two complicated objects, like two images, two text strings, two genomes? But in particular, images is one that I've looked at a lot. Okay, so we're going to play this game. This is a game that, or this is data from this paper DreamSim that we put out recently with Stephanie Fu, Nathaniel Tamer, and Shabita Sundaram as the lead authors. Okay, so here's how the game is going to work. Oh, let me plug this in, and then we'll start. Did I mess it up? Okay. We have it on one screen. There we go. Okay. Sorry, I jostled that. Okay, here's how the game is going to work. So the question is the left image or the right image more similar to the middle image? So which image, the left or the right, is more similar to the middle image? So I'll ask you to clap if you think it's the left image. So go ahead and make your decision. And if you think it's the left image, now clap. 1, 2 people. Okay, now right image, clap. So how did you do that? Anyone have a guess? Like, why did you think the right image is more similar? Is it the cosine distance between the two vectors, between the two? No, right? It's something very complicated. Somehow you just have this gut feeling. Okay, what about this one? Left image? Oops, sorry. Left image? Okay, right image? It's pretty hard to say why. I mean, maybe it's because it's one item and this is like 2 items and numerosity matters a lot. Okay, left image? Okay, a few people. Right image? Let's try that again because you didn't have time to think. Okay, decide, and now everybody clap. Okay, left image? Right image? Okay, that's what we found too. Like, I find it really hard to intuitively say which, like, I don't know what the equation is. If you told me to guess what people would say, I'd be like, well, I would say right, but I don't really know why, so I don't know. But everybody says, everybody says left. Not everybody, but like 9 out of 10 people in the experiments. Okay. So I think if we could understand how to measure distance between data points, then we'd basically be done. I think there's 2 different views on representation learning and self-supervised learning. One view is to learn an embedding, learn some function from data to a vector in Rn. But another view is to learn a distance function that takes 2 different data points and outputs a scalar. And these views are often kind of exchangeable. Like if I have an embedding, I can equip it with some simple norm like L2 distance, and then I get a distance function. If I have a distance, I could maybe find an embedding such that L2 distance under that embedding is equal to my target distance function. So you can often navigate between these 2. But I would say most work, I think, thinks about representation learning in the former sense, learning embeddings. But this talk will think about it in the latter sense. And I kind of prefer the latter sense. I kind of think in some ways it's more fundamental. If you have the distance measure, then you can make predictions. You can use that for make predictions about the performance of machine learning problems. Whereas if you only have the embedding but no associated distance measure, then you don't really have the full story. Okay, so we're going to talk about distances. And the question is going to be, where do distances come from? So without explicit supervision, without somebody telling you, here's the ground truth true distance, how could you come up with a measure of distance between 2 complicated things? And I'll give 2 answers, which will correspond to 2 lines of work that we've been pursuing. One is that you can get distance from statistics. So distance could come from a measure of how statistically independent or associated are 2 variables A and B. And the basic measure we'll use is going to be this probability ratio, how often do things co-occur, divided by how often you'd expect them to co-occur if they were independent. Okay, and the other answer is going to be from physics. This is maybe the more intuitive one, the classical one, like what is distance? Distance is like how long it takes to walk from point A to point B, how much work it takes to change the world from state A to state B. Okay, so let's look at those two questions. Okay, so the first idea is that distance can be derived from just observations of events co-occurring in space and time, or inferred events and observed data. And I'll talk about this Platonic hypothesis that Randall mentioned. So the basic statement of that hypothesis, this is a slightly stronger version than the one that we put in the paper, is that different neural networks under different learning algorithms with different SSL objectives or even supervised objectives kind of converge on the same way of measuring distance, and they converge on the same representation to the degree to which representations are defined by how they measure distance. And then the further thing, as I'm going to argue, and we argued this in the paper, but it's a little bit hidden, is that this particular way of measuring distance is a measure of statistical dependence. Okay. By the way, this can be interactive. I'm happy to just shout out, raise your hand anytime in the middle of the talk. It doesn't have to be questions only at the end. Okay, so this was a paper, a position paper we put out at ICML last year with Minyoung, Brian, and Tongzhou. And we called it this Platonic hypothesis. Okay, so let's get a little more into the details of how we can characterize representations in terms of their distance structures. And we're going to use kernels. So we're going to restrict our attention to the vector embedding types of representations. But the thing that we will be analyzing and looking at is the distances that embedding induces under like an inner product on that space. So the kernel over the representation under this mapping f, x goes to Rn. Okay, so the kernel is this bivariate function. It's a distance function or similarity function. It takes 2 data points in and outputs a scalar. And we will define it with respect to some inner product, like dot product, for example. So we'll have f of xi, f of xj is the ijth entry into the kernel matrix. And we'll evaluate that over not an infinite set of possible data points, but just over a discrete set. So we have a kernel evaluated over a discrete set of data points. So here's an example of a kernel for some cartoons, some emojis, under some vision model. Like this might be a pretty nice vision model because it says that apples and oranges are quite similar under this representation, and oranges and elephants are quite different under this representation. Okay, so kernel methods and the use of kernels to characterize and solve problems is of course a very old and popular idea. It also appears in neuroscience. So people in neuroscience study these representations, but they don't call it a kernel. They call it a representational dissimilarity matrix, but it's the same thing. Okay, so we started looking at this, trying to understand the kernel similarity, the similarity between the distance structures induced by different representations in different models. So here's an example of the kind of thing that we looked at in this work. We looked at how similar is the structure of similarities given to you by dino features versus clip features. And these 2 kernels are similar because they measure distance in the same way. And you can see that visually that this one groups the elephants and the giraffes together and the apples and oranges separately, and they both have that same structure. Okay, so I'm going to actually skip past this comparison because I think that it might already be expected or obvious. Like we kind of know, I think, as a community that the representations learned by clip and dino and other types of things have some degree, like coarse grain similarity. And we can debate about the finer grain details. That could be interesting. But at the coarse grain, they're pretty similar. What I think is a little bit less known and we found more surprising is to look at the kernel similarity between a vision model and a language model. So in order to do that, what we do is we measure the kernel on images under a vision feature, and then we measure the kernel on words, or actually sentences, captions, under a language model. And we match them by saying that the ith entry of the language kernel will be the caption for the image in the ith entry of the image kernel. So how similar is apple to orange will be here, or sorry, apple to orange here, and how similar is the word apple to the word orange will be in the same location in the other modalities kernel matrix. Okay, so the question is, do language models measure distance between sentences in the same way as vision models measure distances between the images that those sentences describe? Okay, so here's the main finding of this work. Or at least I think the most interesting one. So we have a plot of, we're gonna have a lot of different language models and look at their kernel alignment, their degree of kernel similarity with Dino. Okay, you can do this with other vision models. The story will be roughly the same, but we are gonna focus on Dino right here. And as language models move along the x-axis, they get better in performance at language modeling. So they get better in performance at next token prediction on text. So what happens as they get better in language performance? Do they get more or less aligned to vision? Okay, so here's the result. I think you can kind of anticipate it. As language models get bigger, better, as time passes, all of these things are correlated. So we don't know if it's because they have more parameter, more data, that needs to be teased out. But as language models get better at predicting words, they become more and more aligned in terms of how they measure distance with the way that a vision model dyno measures distance. Okay, the trend is also the same in the other direction. So as we increase the quality or the performance or the size, those are again all correlated, of the dyno model, we get higher alignment with the vision models. So dyno small is kind of somewhat aligned, but dyno huge is more aligned, or dyno giant is more aligned. Okay, and then you can see the names of the language models. We're going up to Llama 65B here. And I think there's some nice recent work from Saining and Jan and others, some of you might be here, that showed that if you go to Llama, like if you go even higher, you end up seeing that the alignment continues to increase. So there's a recent archive release from a few weeks ago. This was the one that was scaling self-supervised learning to like internet scale data. Okay. So maybe it will keep going. And I would say that 2 weeks ago, we found out that it does keep going a little bit, but it's actually more like this. Like, I think, there's going to be diminishing returns at some point. I doubt it will just drop off, but that's another possibility. Okay, the title is this, there's a nice old phrase and book title, everything that rises must converge. And that's kind of our basic argument, that as you increasingly get better at modeling the world, then there's this convergent pressure toward all the different representations getting closer to the truth, getting closer to like some kind of Platonic ideal. Okay. Any questions about the empirical results? And then I'm going to talk about a mathematical model of what we think might be going on. Okay, so here is one particular toy world in which you would expect convergence in the kernel structure between a language model and a vision model. So what I've shown is empirically, we see that these different representations are converging. If we can just show that one representation in the family of things that we're looking at is something we can understand mathematically, and we can understand what it converges to mathematically, then the hypothesis or argument would go that that's what everything is converging to, because everything is converging to something is the empirical observation where, that's a hypothesis. And now here's one particular mathematical model of a contrastive learning system that will converge to something we can actually understand a little bit better. Okay, so the model basically imagines a world in which there's events Z. There's some reality out there. And these are discrete events because that will make things simpler to model. And we observe those events Z either with a camera, X, or with text, Y. And the text could be generated by somebody describing the scene, or it could be just, in reality, in our data, we actually use captioning. So it's like the text is actually being processed through the vision modality as well. And we're going to learn a unimodal representation of images and a unimodal representation of text. And the question is, why do those two things become alike? So we're going to assume that the world is governed by some underlying joint distribution over discrete events. It's a time series, so you have time going from 1 to t. All data is mediated by these observation functions. And we're going to model co-occurrences. So we're going to model co-occurrences over the observed data. So this could be, for example, co-occurring patches in an image, co-occurring frames in a video, co-occurring words in a sentence. So you probably will recognize that many of our favorite self-supervised models operate on data like this. They try to model something about aligning or bringing together two data points which co-occur in space or time. Okay, so co-occurrences is like how often does these are discrete observations. How often does discrete observation A occur within a time window adjacent to observation B? Okay, so an interesting thing, this is not novel to this work, but it's been shown in various other papers, is that contrastive learners under the NCE objective are minimized. They converge to, if you have sufficient optimization and capacity, they converge to the point-wise mutual information function. So what that says is that the minimizer of the contrastive objective, if my definition of positive pairs is two co-occurring events, and my definition of negative pairs is two random events sampled from the marginals of the joint distribution, then the best classifier between those two things is just that ratio, that probability ratio. That's called the pointwise mutual information. How often does observation A and B co-occur divided by how often you'd expect them to co-occur if they were independent random variables. So the product is just how often you'd expect them to co-occur if they were independent random variables. And a lot of contrastive learners try to find a embedding in which the dot product is the score that does the classification. So it's trying to make the dot product be proportional to this value, the PMI. Okay, so this is nice because it has a really simple kind of intuitive explanation. So contrastive learning learns an embedding in which similarity is equal to the co-occurrence rate of the events, normalized by this denominator here, but roughly you can think of it how often they co-occur. Okay, so just to give you a picture, the embedding will look like this because apples and oranges co-occur a lot in grocery stores and kitchens, but apples and elephants might co-occur less. And the really interesting thing comes about, well, now this is a model that we can have to understand what contrastive learning is doing under particular conditions. But the really interesting thing is, if you assume that your observation function is bijective and you're working with discrete random variables, then all of these probabilities kind of carry through not only over the observations X and Y, but over the underlying events that generate them. So bijective observation is an unrealistic assumption, but I think it's a good starting point nonetheless. So that just means that the observed data, like the image, doesn't lose any information about the underlying event, the underlying scene. I mean, obviously we know that's not true. Images are not a full, they lose information. They don't show you what's behind, occluded. But I think it might be a good starting point. And then you can relax that, and that should be interesting future work. But if we make those assumptions, then the PMI over observations equals the PMI over the underlying events Z. That means that the PMI over X equals the PMI over Y, which equals what the contrastive learner will learn on vision data, which equals what the contrastive learner will learn on language data. So essentially, oranges and apples, the words co-occur in text a lot because they co-occur at the same rate as the images co-occur in kitchens. And that kind of makes sense because if you're writing a story about a kitchen, you're going to talk about apples and oranges. And if you're not going to talk about apples and elephants as often. Okay. Maybe elephants eat apples. I'm not really sure. This is just an example. Okay, so that's our model. So we're arguing that these systems in some idealized settings converge to the pointwise mutual information function over the underlying events that generate the data. And perhaps this is where all these models are heading. Now, that math doesn't explain MAEs, it doesn't explain autoencoders, it doesn't explain a lot of other types of models. But empirically, we saw that those other types of models are learning similar representations to contrastive learners. So I think maybe there's interesting theoretical work to do to understand why you'd expect that to be, or if that turns out to be like a spurious correlation and actually wrong. Let me show you one demo of this math on a toy domain of colors. So we can actually explicitly measure the pointwise mutual information over discrete colors. So we take a set of images, we discretize them. So you have colors which are one-hot codes like red, green, orange, yellow. They're not continuous vectors. And we calculate just with a tabular probability model, what is the PMI between blue and yellow and red and yellow and so forth. That gives us, we then say that is our distance function that a contrastive learner would arrive at. Can we then do dimensionality reduction to visualize what that distance function looks like if I show the embedding that best preserves those distances? So this is MDS, dimensionality reduction. And the kind of cool thing is that you get like the color wheel. Kind of makes sense. Like blue and turquoise should co-occur more in nature than blue and red. And perhaps this is part of why, or perhaps this is related to why we see color similarities the way we do, because this color space looks quite similar to the color space in which humans perceive similarities, the LAB color space. And you can do the same thing, and this is replication of prior work from Abdu et al., which is a really cool paper. You can do the same thing on language models and ask them, what is the similarity in your kernel structure in some embedding layer of the network of the language model between red and orange and purple and green, and you get a similar organization of colors. Okay. So on a color domain, this PMI model seems to be explanatory. We can also go back to that original question. How similar are these two images, and what could explain why we think that those are, medium similarity? And interestingly, in this paper, what we found is that if you look at different metrics over time, okay, some of these were designed. It's cool that we have, some of the people that did, like SSIM is in here. DIST, I think Arrow is also part of that. It's doing pretty well. So if you look at these different metrics, some of them are designed as metrics and some of them are designed as representations. But again, I'm claiming that those two things are just two views really on the same thing. Over time, you're getting higher alignment with human judgments. So this plot on the y-axis is showing how well do the judgments that the metric given by the model would give you, how well do those compare to what humans say the distance is between two different images. And older, PSNR and SSIM not working so well at this point. But interestingly, these two are kind of fit to human data, so they're supposed to do well. But interestingly, these models like Dino, which aren't fit to human data at all, they do even better. So self-supervised learning has discovered the same perceptual similarity structure as humans came up with. So that's interesting. And to the extent that Flip and Dino and MAEs are all learning similar representations, which maybe are explained by they're ultimately getting to this PMI kernel, then we might have an explanation of why humans see things as similar. Yeah.
Just a little bit more details on the human data.
Sure. Yeah.
This is just random parts of an image graded
against
another random part of an image. Is there any others from different semantic categories? Others just a little bit more details because traditionally it's hard to assess those. From humans. How much that
Right. Yeah. So this is a big question, like in psychophysics, how do you measure similarity between different images? In this, so the full details in this paper, I don't have all the slides for that talk, but the gist of it is these are actually synthetic images. We generate, a few tens of thousands of synthetic images from text prompts. And these two images come from similar text prompts. So that's how you get, you want to make these measurements, not over things that are completely different, because then humans have no idea what to say. How similar is a light bulb to a snake? Well, I don't know. So this is more like mid-level visual similarity. This is the caption that generated this is not that different than the caption that generated that. They're both like a snake. And that's how you get the data. And then you run this with a two alternative force choice experiment. You show a triplet, you show snake. You do exactly the experiment I did at the beginning, and you say which one is more similar. And humans give you that binary data. And then you test if your model would make the same binary decisions. If it thinks that if humans said A is more similar to B than it is to C, does the model think A is more similar to B than it is to C? Okay, yeah, happy to talk more about that, yeah.
So I have this question where I'm not sure if this is too early in the talk to ask this, but there's this philosophical discussion about my red is not your red.
Yeah.
Have you heard of that?
Yeah.
So it's even though we are labeling the same color as red, our actual sensory experience might be quite different. So that makes me think about how can you actually, I mean, I know that you can look at the PMI and all of that stuff, but to actually make the statement that all these models are converging to the same representation, if we can't even, if you and I can't even agree on what red is, how can these models agree on?
That's a great question. I should preface this by saying that I don't believe that all these models are converging to the same representation. That's just a hypothesis, which I think is a nice hypothesis to try to prove or disprove. And I think it's more true than we expected, but there'll be differences. Like I'm not denying that there are differences. I'm just focusing on the commonalities. But in terms of my red is different than your red, that might be true, but perhaps my judgment of similarity between red and blue is the same as your judgment of similarity between red and blue. So the distance, the kernel, is invariant to isometric transformations of the embeddings. You can rotate them, you can permute them, you can do all these different transformations, you can translate them. And that means my red could be different than your red in terms of the vector and like the qualia or anything else, but it induces the same distance structure, and that's all we're saying. We're only talking about distance structure, which is one reason why I like the distances, because they're invariant to those transformations that might not actually matter. Okay, summary of part one, and then we're going to move on to a completely different perspective on this. So different representation learners seem to be somewhat alike in the way they measure distance. We have some hypothesis for stating that this is where things are going, and there's some empirical evidence, but it's definitely not a closed debate. And I'm sure that there will be interesting differences as well. And we can show that one such representation in that family of representation learners that we're looking at under idealized conditions converges to something that we can describe with simple math. And that is the distance converges to the PMI plus a constant. And so the argument for this part of the talk is that learned distances and the kinds of the reasons why we say A is more similar to B than it is to C are somehow reflecting measures of statistical dependence, measures of how much more often these two events co-occur than you'd expect by chance in natural empirical data. Question, yeah.
So I can understand like with color that if like blue is appearing with red, for example, so then they will be close to each other. But how you transfer it to augmentation? Like, the models are not so sensitive to the specific augmentation. So like why we see that why we have like good representation when like it's not clear like why like images that are close to each other like in the representation space are like appear together or like they have like this statistical dependence, like how it's
I think the question is, what about augmentations that aren't just like co-occurrence, like two frames in a video? What about like rotation or some other color jitter? That I don't think I have a good explanation for right now. So I'd say that models, I think that there are certain representation learning algorithms that we can characterize fairly cleanly in terms of co-occurrence and PMI, and there's others where it's much less clear. For example, autoencoders. It's not clear why autoencoders should learn similar representations. Empirically, they actually don't, but MAAs do, and like simple transformations of autoencoders do. So why is that? I think that's ongoing science, and I don't have a good answer right now. Yep. Okay, this is more about like the co-occurrence type of self-supervised learning as opposed to the invariance to transformations type of self-supervised learning. Okay, any other questions about part one? And then I'm gonna talk about the second idea, which is physics. Okay, second idea is, high school physics told us how to measure distance. It's just like the length of the path between two things. Okay, so can we measure distance between two states as the cost of going from state A to state B? And the non-trivial part is we want to make it the optimal cost of the shortest path between state A and state B. So in this part, I'll talk about this work where we tried to measure distance between states for reinforcement learning, where the distance is equal to the optimal value function, the cost of the optimal policy or optimal plan going from A to B. And this was work that was led by Tongzhou, who was also part of the other paper, and also with Antonio Torralba and Amy Zhang. Okay, and we called this method quasimetric learning and then quasimetric reinforcement learning. Okay, so here I want to also pitch another picture for what I think might be a cool self-supervised agenda for the era of agents. And that is, so what should, like self-supervised learning for text or images might be about modeling, doing masked prediction, modeling co-occurring data points, modeling invariance to transformations. What should self-supervised learning look like for agents? And the idea that excites me is that maybe it could be the agent should not have any task, but it should just try to figure out how to do everything that there is to do in an environment. You just put it in a room and it just tries to do everything. Okay, but everything is a little bit too much, so let's make it simpler. Let's say the agent will try, the self-supervised objective will be navigate from any state to any state within an environment, or any state to any goal, where a goal is defined in this context as a set of states. Okay, so obviously, you still have to have some constraints, like you have to have a way of just defining reasonable states, reachable states, but this is the high-level idea. And so in this project, we put agents into mazes like this, and we tried to get them to be able to navigate to different goals. So you could ask the robot to go to the apple or to the diamond. Okay. So the kind of gist of this actually came from a goal, which is to convert reinforcement learning to representation learning. So if I have a good representation, then everything else is easy. That's the basic idea. And can we apply that same idea to reinforcement learning? So can we find a representation specifically, not everything is easy, but specifically in which planning and control is easy? Which of course is an old idea, but that's our starting point. So can we find a representation in which planning is trivial? And how I'll define that here is we're going to try to find a mapping from states onto a embedding, and it's going to be like hyperspherical embedding, so onto normalized vectors, such that the optimal plan to go from state A to state B is a straight line. So the optimal plan to go from the robot's location to the apple in representation space is a straight line. But in actual state space is maybe a more complicated path. And the optimal plan to go to the diamond is also a straight line. So we're kind of linearizing control. Okay. And then if you could do that, you could plan by finding the straight line and then kind of doing the backwards mapping to figure out what path through state space that would correspond to. Okay, so how are we going to do that? So the first observation is that there's kind of a fundamental structure which is really useful to do this, which is the value function. And the particular value function we're using is the goal conditional value function, sometimes called the universal value function. So what is the value? Which means the distance of the optimal plan from the state of the robot to the goal, which is the apple. And here's the value function with respect to the apple defined over all the states. So you can see yellow means the value is low because it takes a long time to go through this path. And blue means the value is high because I'm very close to my goal. So the value function is a measure of distance between state and goal. Okay, the value function for the diamond is different. So the distance, so this is actually just a measure of distance. That's the point. The distance to the diamond is low in the room with the diamond. Okay, so how should I measure the value function for all goals, not just for those two goals? So I'll model V star over state and goal for all goals in some environment, which might be for simplicity, that could just be all states. How do I get from any state A to any state B? And I could use just a neural net, unconstrained neural net, and that should do it with enough data, right? So neural nets can be universal approximators, but we can actually do better because it turns out there's a lot of structure that's shared between different goals. And the particular structure we're going to exploit is the triangle inequality. So the triangle inequality says that for the planning problem, for any MDP actually, but there's things in particular for maze navigation, the planning problem satisfies this, the value function, the optimal value function satisfies the triangle inequality. Okay, so that says that the value to go from state A to state C has to be less than or equal to the value to go from state A to state B and then from state B to state C. Why? Because if the optimal plan to go from A to C were to go through the apple, then this would be equal, and otherwise it would be a better plan. So this is just a fundamental property of Markov decision processes of planning problems, and it's a really nice one because it enforces metric-like structure on the space. Okay, so we could use metric learning. We could learn a distance, and we can constrain that distance to be a metric. So here's one way to do that. We simply have embeddings that we learn, and then we measure distance using a function that we know is a metric, okay, like the Euclidean distance. Okay, so this is how you can do metric learning to model the optimal value function. Okay, but there's an issue, which is that actually the optimal value function is not a metric. It's what's called a quasi-metric. And why is that? Because metrics are symmetric functions, and the value, the cost to go from S to G is not necessarily symmetric. It's not the same as the cost to go from G, where G is a state, to S. So here's the distance from the robot's state, and here's the distance to the robot state. And why are these different? Because this maze has one-way doors. So going from here to here has a different cost than going from here to here, because I can't walk through this door in the opposite direction. To go from here to here, I have to go through this door and then that door and then here. Okay, so the cost to go from state A to state B is not necessarily the same as the cost to go from state B to state A if you have one-way doors. And maybe one-way door seems like a weird special case, but actually this is ubiquitous. I think for almost all MDPs that you'll encounter, all control problems, they're typically asymmetric. So gravity makes it harder to walk uphill than downhill. Escalators and one-way streets are an obvious example. Times arrow is an asymmetry just fundamental to physical control. It's much harder to get up than to fall down. So this robot falling down is an easy problem. Getting up is a hard problem. The world is just fundamentally asymmetric, and we need to therefore model it with an asymmetric function. Okay, so we could go back to our unconstrained neural networks, but we still want to use the triangle inequality. So how do we impose only the triangle inequality, but not the symmetry property of metrics? We can use what are called quasi-metrics. Quasi-metrics are a generalization of metrics to include asymmetrical functions. So we will simply, in this project, learn an embedding such that, and then we'll apply a quasi-metric function to measure distance between the two embeddings. So I'm not going to tell you exactly how to model a quasi-metric function. I'll just say that we have some papers and there's torch quasi-metrics if you want to play with that. But just take it as granted that we're constraining our space to be only a search over quasi-metric functions. Okay, so an interesting thing just to state this more formally is that optimal value functions for MDPs are always quasi-metric functions. So for single task RL, the set of possible value functions, the set of possible mappings from state to scalar is equal to the set of value functions. So there's not really any structure between tasks to exploit, but for goal reaching RL, it's state by state goes to scalar. So it's like a distance function. That's the optimal value function over different possible state to state transitions or state to state plans. And it turns out that all possible state distance functions over this space is a strict superset of optimal value functions, but the quasi-metric subset is exactly the same space as the space of all possible optimal value functions for MDPs. And so we know that the solution to the value function learning problem has to lie in this subset, so we should impose that structure, impose it as a quasi-metric. That will make it more efficient for us to define that solution. Okay, so there's some theory in the paper that kind of makes that more clear if it's not to you. But the recap is that I think that generalist agents or agents that have multitask abilities should be able to reach any reasonable goal from any reasonable state. They should model the optimal value function over states and goals. The true optimal value function is always quasi-metrics. We should impose that structure. We should model V star as a quasi-metric, and modeling as a quasi-metric shares structure between tasks via the triangle inequality. So learning to solve one planning problem informs other planning problems because the triangle inequality relates different plans to each other. So this should be more data efficient. Yeah.
In all these problems, it seems that even though the distances are asymmetric, on some small enough length scale, they would be symmetric. If you're within a room.
Yeah. That's right. Oh, that's good. Yeah, I like that.
Is that something that shows up in your parameterization of quasi-metrics, or is that?
No. I like that idea. So like once you're in a room, you're through the one-way door, it's a metric. And there might be an interesting like hierarchical control problem where you could exploit that. You could do like metric planning within every like local region, but the like global structure is quasi-metric. No, we didn't really look at that. I think that's a nice idea. Okay. Oh yeah. So if you want to apply a quasi-metric function over learned vectors, then this is the toolkit to use. And I think not a lot of people know about this quasi-metric stuff. I think it's really cool. I think it could be something that really leads to a lot of progress. So I would encourage you to look at it. Okay, but I do also want to tell you the reinforcement learning algorithm that comes out of using. So I could just fit my quasi-metric to supervise data of optimal value function, but how do we actually get the data? So we need to somehow fit the thing to something. So here's how you're going to do it. It turns out to have a really simple construction. So here is a environment. Environment can be represented as a graph of transitions between states. Our task is to learn a distance function that's quasi-metric that will approximate the optimal value function to go from any state to any state. So again, I'm defining goals as just a single state, but you can generalize it to be a set of states. And we're going to do this by just learning the graph's adjacency structure and then kind of globalizing. So the cost to go from this to this is going to be, well, I know the cost to go along any edge, and then I'll kind of pull things apart to globalize and find the total cost. So what is that going to look like? So first, we're going to learn, just supervised learning, the cost to go from any state to any adjacent state. So we're going to learn the edges of the graph. Or we could be given this. You can imagine you're given this, but in general, the agent will move around to find this structure. Okay, so the cost along the edges for simplicity is going to be 1, but it could be a scalar. Okay, so given that our quasi-metric function accurately represents the cost along every edge, and given that we've imposed it to be a quasi-metric, so it follows the triangle inequality, then we have the cost between any non-adjacent nodes, like red and green, which are far apart in that graph, is going to be less than or equal to the total cost of any path between those two states. That's a statement from the triangle inequality. That to go directly between two states has to be less than or equal to the cost of going along any of the possible paths, because one of those paths will be the shortest path. So in particular, it'll be less than or equal to the shortest path. And how do we find the shortest path then? We just maximize that inequality. So if we find the parameters of the embeddings that maximize the quasi-metric distance between any two nodes, then that will be kind of saturating this bound. It'll be finding the cost of the shortest path. So this is like the maximization over paths. Min total cost equals the value function, the negative value function. Okay. So I think that gets a little bit hairy to think through, but I have a little physical demo. So this is a graph. Okay. So it's a little bit hard to see, but here's a graph. It has edges and nodes. The colors don't mean anything. It's just construction was difficult to get everything spaced. Okay, so a simple graph. How can I find the shortest path between any two nodes? This algorithm says it's incredibly simple. You grab the node you care about. So let's say I care about this node here, and you grab another node you care about. So here's the state, start, here's the goal. You go like this, and you just pull your hands apart. The shortest path appears. Okay, so the shortest path is the most constraining path under constraints, the edge constraints, when you just maximize how far apart you can push these two nodes. Okay, so this is actually true for shortest paths on graphs. You can make like the subway, what is it called here? Anyway, the New York subway system. You can make a graph of it, take Grand Central Station, take your other station, pull your hands apart, and what will appear floating at the top will be the shortest path between those two states. Okay, here's another one. Let's say I take this node. I think what's the shortest path to this node here? Okay, it's these 3 lengths. That's the most constraining, because the shortest path is the most constraining path on the graph. Okay, so this thing does that exact thing, except it does it for it pulls apart all nodes in high dimensional space, and that provably we can recover the optimal value function. So you don't just try to find the shortest path between red and green, you try to find the shortest path between all states by just pulling apart all states subject to the quasi-metric constraint and the local transition cost, which is like, you can't break these edges. Okay, so the algorithm is actually really simple. You sample states, actions, and next state. You could do that under whatever exploration policy you want, or it could be offline RL where somebody gives you that data. And then you maximize the distance between state and goal for a randomly sampled state and a randomly sampled goal given to you by your explorer, subject to the constraint that you have satisfied the local transition costs and subject to your searching over only quasi-metric functions. So your hypothesis space theta is parameterizing quasi-metric functions. Okay, and this can give you the optimal value function provably. Okay, so summary of that part. I think a nice idea for SSL in the era of agents is try to figure out everything there is to do in an environment. For this problem, the optimal value function is a fundamentally useful distance measure because it converts planning into greedy search. Just go to the locally highest value next state. This measure is a quasi-metric, and we can impose that structure, and we can come up with new algorithms to learn that. And the answer for how to measure distance from this part of the talk is measure distance as like the minimum work you need to do to change the world from state A to state B. It's a very kind of physical way of understanding distance. So where do distances come from? Here's 2 ideas. Each one can be fleshed out in a lot more detail. I think these are, there's like huge fields around both of these ideas. One is distances can be derived from empirical data, just observing how things co-occur and how things are statistically related. Maybe there's like a causal version of this too, but this is just about statistics, not causality. And the other is from physics. I will end there and happy to take questions. Thank you.